In this module, we will be studying about classification and nomenclature of alcohols and phenols. Alcohols are organic molecules that contain one or more hydroxyl groups attached to the carbon atom or atoms as shown in the illustration. By contrast, phenols contain one or more hydroxyl groups attached to a carbon in an aromatic ring. In phenols, the carbon attached to the hydroxyl group is sp2 hybridized. Alcohols and phenols can be classified based on how many hydroxyl groups are present. Monohydric alcohols and phenols have one hydroxyl group. Dihydric alcohols and phenols have two hydroxyl groups, while trihydric alcohols and phenols have three hydroxyl groups. Monohydric alcohols can be classified on the basis of the nature of the carbon atom attached to the hydroxyl group. These carbons are either sp3 or sp2 hybridized. We will first consider hydroxyl groups attached to sp3 hybridized carbons. In a primary alcohol, the carbon attached to the hydroxyl group is linked to one another carbon-containing group or to none of the carbon-containing group as shown in the illustration. In a secondary alcohol, the carbon to which the hydroxyl group is linked is attached to two carbon-containing groups. In a tertiary alcohol, the carbon linked to the hydroxyl group is bonded to three carbon-containing groups. An allelic carbon is a carbon atom bonded to a carbon-carbon double bond. Note that the allelic carbon is sp3 hybridized. An allelic alcohol has a hydroxyl group attached to an allelic carbon. Allelic alcohols can also be characterized as primary, secondary, or tertiary. As we saw before, a primary alcohol has one other carbon group attached to the allelic carbon. Secondary allelic alcohols have two carbon-containing groups joined to the allelic carbon. Tertiary allelic alcohols have three carbon groups bonded to the allelic carbon. A benzylic carbon has an sp3 hybridized carbon bonded to an aromatic ring. Thus, we can describe a benzylic alcohol as having a hydroxyl group attached to a benzylic carbon. The molecules illustrated here are examples of benzylic alcohols. Benzylic alcohols can also be classified as primary, secondary, or tertiary, depending on the number of carbon groups bonded to the benzylic carbon as shown. Here you can see that molecule A is a secondary alcohol, molecule B is a tertiary alcohol, and molecule C is a primary alcohol. Only one carbon-containing group is attached to the hydroxyl bonded carbon. A vinyl carbon is a carbon atom double bonded to at least one other carbon atom. Vinyl carbons, which are also called alkenyl carbons, are sp2 hybridized. A vinyl alcohol contains a hydroxyl group attached to a vinyl carbon. Note that vinyl carbon is sp2 hybridized. Can you classify these structures as allylic or vinylic alcohols? Structure A shows a vinylic alcohol. Note how the hydroxyl group is linked to a carbon participating in a carbon-carbon double bond. Structure B shows an allylic alcohol. The hydroxyl group is bonded to a carbon that is adjacent to a carbon-carbon double bond. Now that we understand the classification of alcohols, let's turn to their nomenclature. The common names of alcohols are derived from the name of the alkyl group, with the YL ending, plus the word alcohol. For example, the alcohol with the formula CH3OH is commonly called methyl alcohol. It contains only one carbon, which corresponds to a methyl group. The molecule on the right has a 4-carbon chain in a straight line. This corresponds to N-butyl alcohol, where the N indicates an unbranched carbon chain. In IUPAC nomenclature, the alcohol name is derived from the alkane name of the longest continuous carbon chain. Drop the E from the alkane name and replace with the suffix OL to determine the alcohol name. The location of the hydroxyl group and additional substituents are indicated by using the number of carbon atoms to which these are attached. Let's look at the same molecules we used a little while ago to learn about common names. In the IUPAC system, methyl alcohol with the formula CH3OH is called methanol. N-butyl alcohol is called butan-1-ol. Give the IUPAC names of these structures. Try to define the names on your own before checking the answers. When naming organic compounds, remember to find the longest continuous carbon chain. Start counting the carbons at the end of the chain, nearest to the hydroxyl group. In molecule A, the longest continuous chain has 5 carbons. Start counting from right-hand side of the molecule, at the end, nearest to the hydroxyl group. Nearest to the hydroxyl group is 1 carbon 2. There is a methyl group at carbon 3. So the correct name of this molecule, 3-methyl-2-pentanol. In molecule B, the longest continuous chain has 8 carbons. If we start counting carbons at the left end of the chain, closest to the hydroxyl group, we see that the hydroxyl group is on carbon 3 and there is an ethyl group on carbon 4. So the correct name of the molecule B is 4-ethyl-3-octanol. Some alcohols have multiple hydroxyl groups. To name diols and triols, start with the alkane name of the longest continuous carbon chain that contains the hydroxyl groups. The E of the alkane name is retained and the ending OL is added. The appropriate multiplicative prefixes di, tri, etc. are used to indicate the number of hydroxyl groups present. Numbers in the name then give the locations of the hydroxyl groups. In the example shown here, the longest continuous chain has 5 carbons. We have to start numbering carbons at the right, closest to the hydroxyl groups. Notice that the hydroxyl groups are attached to carbons 2 and 3. So this molecule is named 2,3-pentane-diol. Alternatively, you may see it written as pentane 2,3-diol. Let us try to write the IUPAC names of these alcohols. Remember to work backwards from the longest continuous carbon chain that contains more than one hydroxyl group. Molecule A has 4 carbon chain and 2 hydroxyl groups attached to carbon 2. Hence its IUPAC name is butane 2,2-diol. Molecule B has 3 carbon chain with 1 hydroxyl group on each carbon. Its IUPAC name is 1,2,3-propane-triol and common name is glycerol. Molecule C has a carbon backbone containing 6 carbon atoms. Counting from the right, there are hydroxyl groups at carbon 2 and 4 and a methyl group at carbon 5. It is 5-methyl-2,4-hexane-diol. Cyclic alcohols are named in a similar manner. Count the number of carbon atoms in the ring. Use the prefix cyclo and the alkane name for the number of carbons in the ring. Drop the E from the alkane name and replace it with the suffix -ol. The location of the hydroxyl group on the ring is considered to be carbon 1. Look at the molecule illustrated here. The ring has 5 carbon atoms. So, this is cyclopentanol. Can you name these alcohols? Remember that the location of the hydroxyl group is considered to be carbon 1. So, start counting there. If there is a choice of numbers, count to get the lower number for substituents. So, molecule A contains a 6-member carbon ring with hydroxyl group and a methyl group. Molecule A is a 2-methyl-cyclohexanol, not 6-methyl-cyclohexanol. Molecule B contains a 3-member ring with a hydroxyl group and a chlorine substituent. Its correct name is 2-chlorocyclopropanol. Molecule C has a 4-member ring with a hydroxyl group and a bromine atom, both attached to the same carbon. Molecule C is 1-bromocyclobutanol. Let's start our attention to the class of organic molecules called phenols. Phen is an old name for benzene, so the benzene containing 1 hydroxyl group is known as phenol. Although the systematic name is benzenol, phenol is an accepted IUPAC name. We can use this as the basis for naming phenol derivatives. Toluene is an important benzene derivative. It has 1 methyl group attached to the aromatic ring. Cresol is the name for toluene molecules that have 1 hydroxyl group in addition to the methyl group. There are actually 3 isomers for cresol. The isomers for cresol can be named as phenol derivatives 2-methylphenol, 3-methylphenol, and 4-methylphenol. We can also introduce the use of the prefixes ortho, meta, and para to name benzene derivatives. Ortho refers to 2 desubstituted benzenes. Similarly, 2-methylphenol shown on the left can also be named as orthocresol. Meta is used to refer to 1, 3, desubstituted benzenes. So 3-methylphenol shown in the center is also called metacresol. Finally, the prefix para is used for 1,4-desubstituted benzenes. Therefore, O-methylphenol, shown on the right, is also called paracresol. In IUPAC nomenclature, dihydroxybenzene derivatives are named as diols. Numbers give the location of the hydroxyl groups. Shown here are 3 examples from left to right. They are benzene 2,1-diol, benzene 1,3-diol, and benzene 1,4-diol. However, the dihydroxybenzene derivatives are actually better known by their common names. Benzene 1,2-diol is known as catechol or pyrocatechol. Benzene 1,3-diol is commonly referred to as resorcinol. Hydroquinone, or just quinol, is the common name for benzene 1,4-diol. Let's do some more practical problems. Give the IUPAC names of the compounds shown here. Remember the location of the hydroxyl group is carbon number 1. So molecule can be named 2,6-dimethylphenol. Its common name is 2,6-xylenol. Molecule B is 4-chlorophenol or parachlorophenol. Molecule C is 1,2,3-benzene triol. It is commonly known as pyrogalol. In this module, we will be studying about the classification and nomenclature of ethers. Ethers can also be thought of as a substituted alkane with an alkoxy or alloxy group. Ethers can be classified in several ways. Simple or symmetrical ethers have 2 identical carbon groups on either side of the oxygen. Mixed or unsymmetrical ethers have different carbon groups on either side of the oxygen. The common names of ethers give the names of the alkyl or aryl groups in alphabetical order, followed by the word ether. For example, the common name of the ether shown here is ethyl methyl ether. If the ether is symmetrical, use the prefix di plus the name of the alkyl group name. Add the word ether at the end. The ether shown here has the common name diethyl ether. IUPAC rules for ether nomenclature are based on descriptions of ethers as alkoxy-substituted alkanes. The larger group is considered to be the parent hydrocarbon. The number gives the location of the alkoxy substituent. This makes the IUPAC system more versatile than the common names for ethers. Consider the molecules shown here. It has a methyl group and an ethyl group. The ethyl group contains more carbons. Therefore, the ethyl group is considered to be the parent chain with the methoxy substituent. In the IUPAC system, this ether is made methoxyethane. Let us try to find the IUPAC names of the compounds as shown here. Molecule A is ethoxybenzene. Its common name would be ethyl phenyl ether. Molecule B has a 5-carbon chain with an ether linkage attached to a methyl group at carbon 3. Thus, molecule B is named 3-methoxypentane. Molecule C contains a methyl group and a propyl group. Since the longer chain has 3 carbons, molecule C is named methoxypropane. Its common name would be methylpropyl ether. Molecule D has a 6-carbon substituted alicyclic chain with an ether linkage attached to the ethyl group at carbon 2 as shown. Therefore, its IUPAC name is 2-ethoxy-1,1-dimethylcyclohexane. Molecule E has a 3-carbon chain with an ether linkage attached to an ethyl group at carbon 2. Its IUPAC name is 2-ethoxypropane. Now let's try to name these compounds. When drawing molecules from names, the parent chain is given last in the name. Remember to work backwards. Molecule 1 is 2,3-diethylphenol. Start by drawing a phenol ring. The location of the hydroxyl group is position 1 on the ring. Then add ethyl groups at carbon 2 and 3. Molecule 2 is 2-ethoxybutane. Start with the butane chain, which has 4 carbon atoms. At carbon 2, insert an ether linkage. Molecule 3 is 2-methyl-2-butanol. Start with the 4-carbon chain from butane. Place a hydroxyl group on carbon 2 and then put a methyl group on the same carbon. Molecule 4 is 2-propane-1-ol. Start with the 3-carbon chain. Since it is a propane derivative, put a hydroxyl group on carbon 1. The double bond starts with carbon 2. The hydroxyl group outtrends the double bond in IUPAC nomenclature. The last molecule is 1,3-cyclohexane dione. Start with the fixed numbering. Put a hydroxyl group on 1 carbon. That position is carbon number 1. Put a secondary hydroxyl group on a carbon atom 2 positions away. In this module, we will be studying about the physical properties of alcohols and phenols. Alcohols and phenols consist of 2 main parts: an alkyl or aryl group and a hydroxyl group. The hydroxyl group chiefly determines the physical properties of the alcohols and phenols. The nature of the alkyl or aryl group thus modify these properties to some extent. The boiling points of both alcohols and phenols increase as the length of the carbon chain increases, as shown here for some primary alcohols. This is due to increasingly strong London forces as the length of the carbon chain increases. Let us find out the effect of branching on the boiling point of alcohols. Let us look at this table. The table shows 3 butanol isomers which all have the same molecular formula. As the branching of the carbon chain increases, the molecules attain a spherical shape and the surface area decreases. As a result, the van der Waals forces of attraction become weaker and therefore the boiling point decreases with an increase in branching. Therefore, among the isomers of butanol, tertiary butyl alcohol, 2-methylpropan-2-ol has the lowest boiling point as shown in the table. Alcohols and phenols have boiling points higher than other classes of organic molecules such as hydrocarbons, ethers, haloalkanes and haloarenes with similar molecular masses. For example, the boiling point of ethanol is considerably higher than that of methoxymethane or propane. Although all the 3 substances have very similar molecular masses. Both alcohols and phenols can participate in intermolecular hydrogen bonds due to the presence of the polar hydroxyl group. Thus, alcohols and phenols have higher boiling points than ethers or hydrocarbons, which cannot participate in hydrogen bonding. Alcohols and phenols can both form hydrogen bonds with water, and so both are water soluble. The solubility of substituted phenols is very low in comparison to phenol. It should be noted, however, that as the alkyl or aryl groups get larger, the solubility decreases. Ethanol and other low molecular mass alcohols are completely miscible in water. They can dissolve in water in any proportion. Here are some molecules. Now, in order to find which molecule will have higher boiling point, we essentially need to determine which molecule in each pair has the stronger intermolecular attraction. For set A, 1-hectanol has the higher boiling point because it has the longer carbon chain. For set B, 1-propanol has the higher boiling point. 1-propanol with its hydroxyl group can participate in intermolecular hydrogen bonds, while the ether methoxyethane cannot. For set C, 1-hexanol has the higher boiling point. Its carbon chain is unbranched, giving it stronger London forces than the branched chain in its structural isomer 2,3-methylbutane-1-ol.
Bora, vamos fazer o bora com maior.